I've been getting a bit too stuck into GeoGebra for my own good, and I think in general I'm going to start releasing these videos around 11 instead of 10 o'clock. That does mean that you've got your normal video at 10 for A-level maths, and then you'll have this video around about 11 o'clock as well. So I did make an announcement yesterday about this, but just in case you didn't pick that up for whatever reason, we're not going to do any more mechanics this term. Sorry to mess you around with this. Basically, Miss Hughes and I had a long chat yesterday about various things. One of those things being that unless there's any crazy changes in timetables, which there shouldn't be, Miss Hughes is going to replace me as one of your teachers next year. Mr. Clark Carroll being the other one. And we decided that actually the best thing for us to do in the time we've got left is for me to do some of the pure from year 2, which we can do, and there's quite a bit which we can do from the year 2 pure. And Miss Hughes will start doing the mechanics with you properly in September. When I say properly, I mean as in mechanics is a lot easier to teach when you can show people props, because mechanics is obviously modelling the physical world. Also, Miss Hughes is a lot more experienced at teaching mechanics than I am. I think you would probably actually get a better mechanics teacher for sure by having Miss Hughes instead of me. And simultaneously, I'm probably better at teaching this particular pure stuff than Miss Hughes probably is. But probably not much different, to be quite honest. However, Miss Hughes is definitely a lot better mechanics teacher than I am. So I think it will be a better all-round experience for you guys. I think you'll get more out of it, and yeah. So that's essentially some of the reasons why we've decided for this to happen this way. So we're going to go through some of the pure content from year 2. I know you haven't got the books. I will take photos of the pages as we use them and put them on class charts. We will be buying the pure 2 books for you ready. However, also we won't be able to hand them out until we see you guys again. Heaven knows when that will be, hopefully next half term. That is just speculation, by the way. I have not heard that from anyone. But hopefully next half term, because I'd like to see you before I leave. Anyway, today we're going to be looking at some more vectors. Yay, I hear you scream. We're going to start looking at the vector equation of a line, which is quite exciting. And we're going to do some GeoGebra to just see how this works. Okay, right, so I've got lots of clicking to do, and hopefully I get this right. So here I've got some vector. This vector is called vector D. As you can see, it is the vector which goes 2 along and 1 up. So it would be written as 2, 1 in vector notation. Now what I can do with vector D is a few things, he says as he crazily looks at all of the stuff in front of him. Yes, I can put that in, and let me just move that slightly. And that was a good stop, wasn't it? Okay, so what I've done is I've drawn another vector on top of D, which matches D exactly. However, what I'm going to do is I'm just going to times the vector D by some constant lambda. So there's the vector D, I'm timesing it by, this should say a dot really, I'm sorry about that. So lambda times D is equal to 2.22 times, that should be a times the vector 2, 1. So this lambda is just some constant, and if I change lambda, all I end up with is either a very long vector or the vector gets increasingly shorter. Obviously, if I wanted to make lambda negative, then D would start going in this direction instead. It would just be the reverse vector. So what I hope you guys can see so far is the fact that if I have some vector D, what I can start to do is actually trace out a straight line. If I play that on, I just start to get this straight line here. And if I just get rid of that now. And hopefully also what you guys can see is by by just thinking about this is saying to yourself, okay, well, what is this straight line going to be? We know the vector's 2, 1, so we can think about what the gradient is, and we can also think about what the intercept is. So have a quick, just pause the video now quickly and just see if you can decide what the equation of the line is. So just looking at the equation of the line, what's it going to be? Y equals, it a half x, is it going to be? Oops, daisy. Half x plus 3/2. Okay. So this vector seems to be drawing out this line at the moment. Obviously, if I made lambda really, really big, it would cover all this stuff here. And if I made lambda really small, it would go back down here. I've just lost the trace for some reason. But it lets me move up and down this line. So you might say, well, if I have this vector and I just times it by lambda, does it define this line? And the answer is no, it doesn't define this line. It defines any line that is perpendicular to it. Right, after some editing, I'm back to this. So obviously I can see if I change this intercept, but I have a gradient of half, this vector would probably fit on all of these lines. So what's important is to get the line I actually want is I actually need to put this vector in the right place to start with. Now I've placed it here, but vectors are, if you're doing a sum of vectors, you always need to measure them from the origin 0, 0. Here I've just put it in random space. So what I need to do is I need to think about, if I want to define this line particularly, I need to get myself to this vector in the first place. The way I'm going to do that is by having another vector, v, and not vector v, vector a, and this vector a takes me from the origin to the start of vector d, and so you can see that a has got a vector of 1, 2, and then what I need to do is I need to add on this lambda d, which lets me move up and down the line. So what we're saying is that the equation of a line can be represented in this format here, where we have essentially two things going on. We have this second bit which sort of acts as the gradient, and then you times it by something called lambda just to get up and down the line. And then this first bit you kind of think of as the intercept, but it's not necessarily the y-intercept, it's just a way of getting you to the line. So the equation of a line in vector form is a vector which gets you to a point on the line. So this is a point on the line. Let me just put the line back on. So it gets me to the line in the first place, and then this second bit lets you move up and down the line. Okay, so let's write some stuff down to do with this. So it's vector equation of a line. So what we've specified so far is that if we have the vector equation of a line can be written as this. So this is a point on the line. So as in, no, sorry, say that again. This is the line in total. So this is sort of like the y and x values. This vector here gets me to the line. This vector here moves me on the line. In conjunction with lambda. So this bit gets me to the line, this bit altogether moves me on the line. Okay, and lambda is just a scalar. A and D are vectors, lambda is a scalar. Okay, so for instance, if I had let's have r is equal to 2 minus 1 plus lambda 2, 4. I could say to you, okay, well, what value, so what point on the line do I get to when lambda is equal to 3? So when lambda equals to 3, the point we get to is going to be 2 minus 1 plus 3, lots of 2, 4. No, Max. So how I can read this is, if I wanted to find out what the coordinates of the point I get to is, well, r is the x and y values. I've got 2 minus 1 plus 3 lots of 2, 4, so 3 lots of 2 is 6, 3 lots of 4 is 12. And so the x value is going to be 2 plus 6, which is 8. And the y value is going to be minus 1 plus 12, which is 11. So I could get to other points on this line as well by just changing my value of lambda, but this equation of the line gets me onto the line, lets me move around the line. The lambda lets me get to different points, and if I stick values of lambda in, it gives me a point on the line. So for instance, in this case, I've got 8, 11 when I've stuck in lambda is 3. The reason why r is labelled as an r is because it's the resultant vector of these two bits when they're added together. So the resultant, when I add this vector to this vector times by scalar, gets me to the point 8, 11. This is the coordinate 8, 11, or you can think about it as the vector 8, 11. So there's an example showing something similar to this in the textbook, which I'll take a photo of and send through to you, just so you can see a picture of it. I won't bother drawing a picture now. So one thing we might want to do is say, if I've got the equation of a line in vector form, what is it in Cartesian form? So let's try an example of this. So using the same vector, r is equal to 2 minus 1 plus lambda 2, 4. The way to convert this into Cartesian form is by writing r out in terms of x and y. And then splitting this vector up into its component parts. X is equal to 2 plus 2 lots of lambda. And y is equal to minus 1 plus 4 lambda. From here, hopefully you can see that if I rearrange this top one, I get lambda is equal to x take away 2 over 2. And for this one, lambda is equal to y plus 1 divided by 4. Now, because when I do this vector equation, I stick one version of lambda in, lambda stays constant here as well. These two lambdas have to be the same as each other because they're just this lambda here. And so these two lambdas are equal to each other, so these two bits on the right hand side must be equal to each other. So therefore I've got x minus 2 over 2 is equal to y plus 1 over 4. Is that right? Yes, it was. So what you can do is you could make this into y equals mx plus c form or something similar, or you're absolutely fine just leaving it as this. Okay, so leave it as this if it asks if we're in Cartesian form. If you want to go further, you can, but it really isn't necessary. So this would be okay for it to be in Cartesian form like this. Okay, we've done some two-dimensional examples, and we use GeoGebra to look at it in 2 dimensions. but you can also do it in 3 dimensions, and everything we've done so far works exactly the same for 3 dimensions. So, for example, if I wanted to find a Cartesian equation for this line here, or this plane, well, I've just said a plane, it's still a line. So this line in 3 dimensions, I do exactly the same as before. X, Y, Z is 3, 4, 1 plus lambda 2, 3, 6. And then I separate each one out. X is equal to 3 plus 2 lambda. Y is equal to 4 plus 3 lambda. And Z is equal to 1 plus 6 lambda. Rearranging all of those gives me lambda is equal to x, take away 3 over 2, lambda is equal to y, take away 4 over 3, and lambda is equal to z, take away 1 over 6. Is that right? Yeah. Therefore, the Cartesian equation for this line would be, and this looks rather clumsy, x minus 3 over 2 is equal to y minus 4 over 3, which is equal to z minus 1 over 6. And this is obviously something you guys won't have seen before. We've got 2 equal signs in the equation. This is perfectly acceptable, and this is what the Cartesian equation would be for a line in 3 dimensions. Now, this works really well. However, some people may have spotted a slight issue that might occur sometimes with these examples. You'll notice this, the denominators in these fractions 2, 3 and 6 come from this vector here. And in some books you'll find that they just say, oh, to write this like that you just stick things in certain places, but I'd rather you write it out like this every time, because it means that you don't have to remember a formula, you just understand how these things work. However, if the denominator is 2, 3 and 6, there's nothing stopping this vector having one of these entries as 0, and that would cause an issue here because we obviously can't divide by 0. So if we had a special case, so for instance let's take the same vector equation, 3, 4, 1 plus lambda lots of 0, 3, 6. So you might want to write these all out again, which is absolutely fine. We get x is equal to 3 plus 0 lots of lambda. We've got y is equal to 4 plus 3 lambda, and z is equal to 1 plus 6 lambda. So the vector equation for this one, well, I would still stick these together. I'm not going to do it again because it's already up here. The Cartesian equation for this one would be x equals 3 and y minus 4 over 3 is equal to z minus 1 over 6. Essentially what happens with this is it becomes a line in 2 dimensions. These two depend on each other. There's only 2 variables, so this is going to be a line in 2 dimensions. And it's going to exist in the plane x equals 3. It would probably be easier if I actually pick the z value instead. If I pick this as 0 instead, you would probably see this a bit clearer. So if I pick this as 0, then I'd end up with z equals 0 and y is equal to x. That's just the standard Cartesian plane when z is equal to 0. If you set z equal to 1 or z equals 2, etc., 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 you'll just get the Cartesian plane lifted up or down the z-axis. I hope that's fairly clear. It's not terribly important. It's just to be aware that if you have got a 0 here, you can't go through this process. as well. Well, you do the same process, but it's just to be aware that this bit here might throw you, but it shouldn't do. You just need to write this down and the other bits there together. Okay, so what we want to have a look at next is how can we go the other way. So we might be given a line written in it's a three-dimensional line written in Cartesian coordinates, in Cartesian equations, sorry, and we might want to write this in vector form. So essentially just undo the process. So feel free to have a quick go at undoing the process now. And if you're unsure how to start it, remember how we got here. This is equal to lambda, this is equal to lambda, and this is equal to lambda. So if I write those out, lambda is equal to x minus 4 over 3. Lambda is equal to y minus 3 over minus 2. And lambda is equal to z plus 6 over 4. Altogether, if I rearrange this, this becomes x is equal to 4 plus 3 lambda. Does that work? Take away 4 divided by 3. Yep, that's good. Y is equal to 3 minus 2 lambda, and z is equal to minus 6 plus 4 lambda. Bringing that all together, the equation of the line is going to be 4, 3 minus 6 plus lambda lots of, and this is where some people make mistakes often, so we've got a plus there, we've got a minus there, and we've got a plus there, so this is going to be 3 minus 2 and a 4. And that's how we go back the other way. Okay, so I've just got some fairly straightforward exercises for you to do today, and we're going to look at using these ideas in a lot more different ways tomorrow. Can you do exercise 1.1, questions 1 to 5? And I'll speak to you again tomorrow. Cheers, bye-bye.